Tracing its roots back to the early 1900s, Heat Transfer Products Group and its brands Russell, Witt, Kramer, and Cold Zone have built a reputation for quality and efficiency in commercial refrigeration. And today, we're proud of our bold commitments for 2025 to dramatically reduce our impact on the environment. We are committed to addressing the labor shortage and increasing training needs facing our industry. And we see a future with zero waste in the use and manufacturing of HTPG products. That's why we are designing for zero waste. We are reimagining our products to dramatically reduce their greenhouse gas footprint, refining our processes to drastically reduce our carbon footprint and landfill waste, all while training plumbers, contractors, and key influencers on how to install, monitor, and maintain sustainable products to perform as efficiently as possible. From the very beginning, we've integrated sustainable thinking into everything we do. And as a member of a global family of brands, we will deliver greater performance while contributing to something greater than ourselves. Creating solutions that truly make a difference, delivering a greater degree of good.
Well, hello, HVACR Village. Thank you all for joining us so much. We're going to spend a little bit of time this week changing our topics slightly. We've spent a lot of time on the technology transition, the refrigerant transitions. And Ty, I know personally, I didn't realize how hard it was to teach someone a topic until I knew it very, very, very well, right? When I was in the field, I could take a principle that I was, fairly experienced with, but then when I was asked to actually teach someone that topic, man, that's a whole nother story, don't you think?
100%, absolutely. You have to understand it to a whole nother level if you're going to explain it to somebody else.
And, this might be the very basics, the fundamentals of refrigeration, but I really hope you all get as much out of this as I did myself when David Harrell. David, how are you doing, sir?
Doing good.
When David went through this with us the other day, it reinforced that mentality of you really need to know something well if you're going to teach it well. And it's as important to know these new technologies and transitions as it is to have a good understanding of our fundamentals. And so we're going to spend some time today diving into the fundamentals of refrigeration, because really refrigeration is at the core of everything we will ever touch in our career, from the littlest of single can refrigerator to the largest of industrial refrigeration factories. We're going to encounter the same principle. Mr. Johnson, thank you for joining us, sir. Glad to have you here. And everyone, let us know where you're joining from. We love to know how large this community is growing. And if you have any questions along the way, have any comments, you have something that we need to dive a little bit deeper in, please do that. We have the right people here today for that. So, yeah. So, Mr. Harrell, tell us a little bit about your history in the industry before we start diving into this lesson.
All right. I got started in this industry about a little over 30 years ago. Mm-hmm. And honestly, I got started in this industry because I was not a very good high school student. Ate up with ADHD, and I see Ty waving and Clifton waving, and this should be fun because this is going to be like three of the most ADHD people I know hosting a class.
This could be the Three Stooges refrigeration course, by the way, everyone.
But if nothing else, it'll be fun, right?
It is, absolutely.
But yeah, I found out my senior year of high school that I could get out of school in a half a day if I had a job. So I found a position hanging duct with the company, or actually a man and his wife who that's all they did is they installed HVAC, and I helped them hang duct at the after school. That's how I got started. The funny thing though, when I got out of school, or graduated high school, I did the one thing I thought I would never do. I went to tech school. I went right back to school. But this industry, just from that hanging the duct work, a little bit that I did, it caught my interest and I wanted to learn more.
Yeah, and I think when we get that bug, it's done for. And yeah, Marvin Van Johnson, you're right. This is the Four Stooges, and it's growing. And so, Patrick Murphy, thank you for joining us. Sean Smith in Illinois, Paul Leonardi, we're so grateful for you all being here and taking time out of your week. And I know you probably all can run through the refrigeration fundamentals and refrigeration circuit. But hopefully, we're going to spend time on things today that you may have forgotten along the way, because we tend to do that. David, we got into part of a conversation about how sometimes in our careers we become idle, and
Yeah,
reasons for that.
yeah. I was when we were talking through my observations. Again, been in it a long time and held a lot of positions, and I've been a technical service manager, the help guy from factories that, to go out and help contractors on job sites. And I've been that person as well. And something that I've noticed in my observations is that a technician, brand new, right out of school or just starting on the job, is interested. He's a sponge. He's absorbing everything. He's learning. I would call him a good technician because he wants to learn. And even if he makes a mistake, he learns from it. He doesn't tend to repeat it, and he's growing. Then at some point, we run across a wall. I say we because I'm guilty. I think all of us are guilty at some point. We run into a wall where all of a sudden we're not growing, we're not learning, we start struggling. We start missing some of the most simple things. And it's because we start forgetting about the fundamentals. And once we come back to those fundamentals, if we survive that struggle, then we start growing again. Right? We don't build a house without a firm foundation, and that's what the fundamentals is to our career. It's the foundation that we build on.
Absolutely. As educators, as instructors, we all go through the same thing. We all get to points where we stop and go, I don't know, I'm just not progressing. I'm not getting better. My classroom isn't growing. Do I need to get a little bit better at something? And sometimes it's as simple as re-looking at our fundamentals, because we may find something and we go, oh my goodness, I forgot all about that. That is the icing that I need to add to my cake. And so we're going to cover some of that today.
Yep.
So hang in there with us, and we sure will.
Interesting story. I was doing the full-blown version of what I pulled out for this class today in Phoenix, Arizona, and had a gentleman walk up to me at first break. And first words out of his mouth were, I've been doing rack refrigeration for 30 years. And I thought, here we go. Well, fundamentals class, he's about to wear me out. Right? Yep.
I'm getting worked.
That's right. And then he stuck his hand out and he shook my hand and he said, thank you for this class. I wish I'd had it 30 years ago. Things that I have been doing for 30 years are making sense now.
Wow.
He had just been doing what he had told to do when this happens. He really had no idea why he was doing it.
Absolutely.
So I think that's a testament to how bad a fundamentals is needed in our industry and reviewed constantly.
Well, I get people that come to me and they say, well, you're the fundamentals guy. And I'm like, well, there's a lot of stuff I really enjoy teaching. It's just the fundamentals are so important and they're so overlooked. And fundamentals is everything we do. Once you get that down, you're unlimited what you can go on. So it's interesting how many people just want to overlook the fundamentals, but it's the foundation of everything we do, and all the problems that we run into really goes back to being fundamentals. When I'm on tech support helping people out, which if you've never done that, give that a try. But a lot of that just really goes back to the fundamentals, getting them to see the refrigeration cycle. Once you can visualize that refrigeration cycle, you can think about where the refrigerant's at, where your superheat's at, where your subcooling's at. Man, you can then solve a big part of what's going on with that system. And sometimes we just get so hung up on the numbers that we forget that that's just a representation of that whole entire system, the fundamentals.
Yeah, right. No, absolutely. And Lacey, thank you for joining us from Northern California. Glad to have you here with us. All right, so let's dive into some fundamentals and see if we can't retrain our brains a little bit.
So from here, I would like to give just a little bit of background as to why I built this program. So I've been with HTPG about 1.5 years, and I was actually brought in to build a training department.
Yep.
And so I'm trying to figure out what should my first thing be. What do I want to do first? What's first? And my wife was actually the one who got tired of me asking the question and storming around my house and from my home office trying to figure out what I was going to do. And she said, what do you keep saying your industry needs? I said, fundamentals. And she said, then go back to your office and write a fundamentals class. Well, I work for a refrigeration company now, so I
Yeah.
had to tie it into refrigeration. And one of the things that I was asked during my interview process is how do we bring or get the interest to get more people in refrigeration? I heard an interesting stat from somebody I consider very trustworthy. Most people that's here know him, but he says for in the refrigeration, the medium and low temperature application, for every 17 people we lose, we're only replacing one.
Wow.
Wow.
That
So
is pretty,
that's a huge.
yeah, much more
So
significant than residential like commercial AC work. Yeah.
so I wrote this program with the thought of how do I show that guy that's in refrigeration or air conditioning that has thought about refrigeration, but maybe he's a little, I'm going to use the word scared of it.
I get those comments and questions on social
Okay.
media all the time.
So how do we get that interest, or even somebody who doesn't necessarily have field experience but wants to get their horizons expanded? So that's how I wrote this and kept it in mind. So I go through the fundamentals, and right towards the end, I will show how I transition to some things that you may not see in air conditioning that you'll see in refrigeration. So
Absolutely.
with that, um, my bio card, that's in the front of every one of my presentations. There's some things on there that I'm kind of proud of, and one being back involved with Skills USA.
Yeah,
I've
love
been out
that.
of it for
Thank
a
you.
while, and HTPG fully backed me, and we now sponsor the refrigeration competition, which is
Yeah.
pretty awesome on my end.
Yes, love that.
So in front of every class, I put very specific objectives up, what we need to do. So you can see how simple these objectives are. But this lays out what the key points and tries helps keep people focused. So one of the things I like to do to keep people involved is ask this question: what if there were no refrigeration?
Yeah,
So
real life scenarios.
Ty, give me a scenario. If there was no refrigeration, what does that world look like to you?
Well, we're immediately going to have a loss of life because the world has what 8 billion people now, the largest population we've ever had in the history of the world, and that's only possible because of refrigeration and transportation. So if we lose the being able to keep that food cool as we ship it across the world, ooh, it's I don't even want to think about that.
Wow, that's a good one, Ty. Nobody's ever brought that one up. So
Yeah.
Clifton, you got one?
I do. Well, I just think about like the expansion of people. Many people don't realize that the Western migration, like when we landed on the East Coast and we made our way to the West Coast, it was only possible because we were chunking ice out of frozen lakes up north to help preserve our food to get us along the way. And then later, refrigeration took over that process so that we could keep our foods to be able to last for longer periods. So without that, I mean, I think about, how far could I travel without refrigeration of some type?
I like that. I like that one.
Right.
And you mentioned out west. I moved to Phoenix, Arizona for 2 years.
Mhm.
Without air conditioning, you could not live out there.
Right.
It's
Understood.
not possible. So I came up with some stuff when I asked myself that question. Some of them pretty interesting. Within 2 hours, perishable foods start going bad. I like the little black box down there. 1.3 million pounds of dairy product are gone within 2 hours.
Wow.
That's a lot of wasted foods.
You ain't kidding, that is.
Most of the internet goes dark. Think about it. We're doing this over the internet.
Right. From the heat from all of the servers that are
Yep.
cooled by refrigeration and
Think of how
technical.
much we depend upon the internet in our everyday life.
Yeah, for sure.
Supermarket shelves become empty within 2 days. We've kind of lived that already, right? We lived that with COVID, and from some of the news reports I'm seeing, people are frightened. They're beginning to do it again.
Yeah, absolutely. I was mentioning before, a lot of people don't realize that we haven't created generators large enough to maintain the refrigeration systems at our grocery stores since the 80s when we left those small mom and pop shops. So all of our larger grocery chains, those generators that sit outside, that's just for backup lighting and for computers. That's not for refrigeration. So
Interesting.
we
Interesting.
lose that power. We lose a lot.
And this one kind of ties back into what ties into Ty.
I love it.
Medicine shortages within a month. A lot of medicines have to be refrigerated.
Sure.
hospital mortality rates go up. So refrigeration, and that's all applications from high temp, medium temp, low temp, cryogenics, you name it. They're all important to our lives now.
Yep.
So what is refrigeration? Refrigeration is simply the process of moving heat, right?
Mm-hmm.
We take heat from one place and move it somewhere else, or one substance and move it somewhere else. And then I like to tie in the refrigeration. In my full-blown class, the refrigerant is the fluid that we use to move the refrigerant. We'll lead into a short discussion on properties of refrigerants, what type of refrigerants, a very brief discussion on A2Ls. That's a full-blown class that's coming in the near future, but it's not there yet. But there's some interesting stuff to help the refrigeration side get prepared. We got two types of energy we deal with, right? Heat is nothing more than an energy. We've got sensible heat. That's heat that can be felt and measured. I'll ask somebody in the classroom to define latent heat, and it's amazing how everybody's eyes drop to the floor. Nobody wants to make eye contact because they're afraid I'll ask them what the answer is, right? Now, you will find that I really like to keep my answers to questions very simple and short. I'm a firm believer in keep it simple.
Yep.
So latent heat is simply causes a change of state without a change in temperature.
Yeah, we do a lot of road trips, and we see that very often. We keep the thermostat right about 75 as we change from one state to another in the car, and it's latent heat, right?
Yep, latent.
Changing state, same temperature.
I knew where he was going. I've heard you say that.
David, you got to watch this guy. There's times where between him and Eugene, there's times, especially we go to like a conference, I'll be laying in bed trying to go to sleep and go, oh man, I missed it. Oh my gosh, they got me again.
Yeah, no, I've heard him say that one before. Oh me. And there's some definitions I think, when we were discussing this the other day, was absolutely surprised at how many people measure superheat but have no idea what superheat is.
What it actually is.
Other than a number, right? Well,
yeah.
The data plate says I need X number of superheat. Well, that's really not telling them anything. Superheat is heat added to a vapor. Again, very simple, but my state has become all vapor and I add sensible heat to it. That's superheat. It's not possible to have a negative superheat. What Ty mentioned the tech support, and I've been in that role too. It's amazing how many times you'll get a call, somebody says, I have a negative superheat. And there's only one answer. No, you don't.
Right. You got a bad calculation or you got a thermistor that is not reading properly.
Right. And subcoolant, again, keep it simple. It's heat removed from a liquid.
Mm-hmm.
And saturation is the point where we're changing state. So I've got liquid and vapor together. I'm changing state. I'm either going from liquid to a vapor or vapor to a liquid in our industry.
There's a lot of questions that we get about glide and, what is glide with a blended refrigerant? That's right. We're gliding between two different saturation points. That's really what we're doing. So when we have a blended refrigerant, we just have different saturation points for those different refrigerants. And in between them is our actual glide.
I was just looking at that comment that popped up. So negative superheat.
Right. I'm so grateful you all are having fun and joining us. It's serious topics, but we are here to have fun and enjoy this.
Absolutely.
And share information with other fellow instructors and learners and educators.
Yeah. And then BTU. I'm always constantly amazed at how many people know that stands for British Thermal Unit, but can't define a British Thermal Unit.
Right.
Right. And again, keep it simple. The amount of heat energy required to raise 1 pound of water 1 degree Fahrenheit. That definition goes on for about 500 more words if we wanted to take it out, but that's enough for what we need to do.
In its simplest form. Absolutely.
Right. So with that, we go to this chart. And we're going to look at taking a pound of water from 32 degrees to 218 degrees, or 212 degrees, I'm sorry.
Sure.
So from 32 to 218 is 200 and, I can't see my own slide.
180 degrees difference.
180, thank you.
Yep.
So if there's 180 degrees of 1 pound of water, that means there's 180 BTUs, right?
needed to move that 1 pound of water from freezing to changing state again.
Correct. So at
Okay.
212, our water starts to boil. Once I develop that bubble and I start boiling, my temperature doesn't change anymore. Put a pot of water on the stove, bring it to a boil, put a thermometer in it, and watch it. Once it starts boiling, your thermometer will not go up until all the water's boiled away.
Yeah, it's a great visual for the classroom to use a little. I've got one. I can't believe I didn't grab that. Just a little electric heater pad, a little electric warmer. Put the water in it, raise it up to temperature, and it's a good opportunity to see that in class without flames.
But that takes a tremendous amount of heat energy to cause that to happen. A tremendous amount of heat energy, right? So we get that 970 BTs of heat energy to make that change of state occur. It's a tremendous amount of heat energy. Once all the water's been evaporated to a vapor, now I can start adding sensible heat back to it. Right? So if I add sensible heat to a vapor, what did I say that was?
Well, it's heated above its saturation, and so it would be above heated or superheated.
There you go.
Okay.
So it's superheated. Now,
if I were Paul, that's a great comment. I'm glad you mentioned this. So Paul Leonardi was asking why we didn't have ice on it, and I remember you explaining to me before just on this particular slide.
Yeah, I didn't include it because when I'm in a classroom, I'm just talking about the refrigeration cycle here. I'm not necessarily talking that it is a theory, but it's not a really deep theory. I'm just talking about the refrigeration cycle. And if I've got ice inside my refrigeration cycle, I've got problems.
You got a problem.
So that's why I don't include. I do know that graph goes on, and when I was doing different classes to where I was teaching a lot more theory and not necessarily into the refrigeration cycle right here, I did include the ice and the BTUs in steam as well.
Sure, absolutely. So just breaking down that graph just to get the fundamentals. Most people would recognize water and steam and visualize that change pretty easily, but yes.
It's so important. So many people miss that latent heat. You figure it's 970 BTUs to make this change state from a liquid to a vapor, but it's only 180 to make it go from 32 to 212. So if I was to pour 32-degree water on somebody, they could feel that. Then if I was to then heat it up to 212 and then pour it on them, that's a huge difference. But BTU wise, that's only 180 degrees difference. 970 on that change in state. And that's where we lose track of that. And on that refrigeration side, in that evaporator coil, we need that refrigerant boiling, changing state to absorb that heat. And that's where people, when they start looking at just pressures alone, they miss the fact that, hey, how much liquid's in there? How much liquid's changing state? How much heat are we actually absorbing? So that latent heat is everything. That's the magic of HVAC right there.
Yeah,
I agree.
So this one chart is the one that caught my attention when I was in tech school that really made me want to keep going and keep going and keep going. So
sure.
I was telling you guys, in my mind, that chart, if you want a very simple chart of what we do in our industry, that's it.
That's it. I agree.
So I was coming from the superheated vapor and going back the other way. That's happening in our condenser. And if I'm going from a liquid to a vapor, that's what's happening in our evaporator. So that chart is extremely fascinating. I can talk about it a lot more than we got time for in here today.
Sure,
but
absolutely.
I love that chart. It's an amazing chart to me. And then there's some laws of physics that make all this work for us, right?
Sure.
Heat always goes to cooler area, warmer to cooler. Right?
Mm-hmm.
I always say hot to cold, but then somebody always says, but I thought there was no such thing as cold. So I try to say warmer to cooler.
There you go.
Right?
That's a good reference.
High pressure always goes to low pressure.
Indeed.
Right. And I tell people, you prove this stuff. Just don't take my word for it. If you want to know about pressure, blow up a balloon. The higher pressure inside that balloon keeps its shape. Let go of it. The high pressure goes to low pressure, and that balloon flies all over the room.
You betcha it does.
Especially connecting with students, having a piece of metal and like a piece of carpet and ask them which one's hotter and which one's cooler, and they'll touch the metal, and people will always say, the class will always say, oh, the metal's cooler. And it's like, oh, let's stop. Let's think of thermodynamics. What's really happening? And then once they start applying that to what their everyday life is, it really changes that. And then the same thing with on the pressure side. If you can get a micromanometer and show that that's how we're moving the air is actually pressure difference, they start really getting to see what's happening. And it's the same thing with the refrigerator. You can put a micromanometer in the refrigerator and open it up. You can see the pressure difference. And it's pretty cool once they start seeing these laws of physics, and applying them to everyday life.
Yep.
Right. Right.
And I absolutely love your last one. That's one of my favorite ones.
When the pressure is raised on a substance, saturation point's raised. That's that dashed line we just looked at in that last one. And then when we lower pressure on a substance, saturation point's lowered. So we manipulate where that dashed line happens in order to reject and absorb heat.
Yeah, my mason jar of water with a vacuum pump is always one of the funnest demonstrations in class for people to see that we can actually cause water to boil. We can change its saturation point by changing its pressure. Very, very fun demo to do in class. Tony, thank you so much for joining us. Yeah, and taking time out of your busy life. Tony is down in North Carolina right now cleaning up so many lives, dedicating. I mean, I don't even know that he's getting any sleep, I'll be honest with you. And then yet he still hops on shows to learn and become better. So,
Thank
Tony,
you,
we're praying for you, Tony.
Absolutely, we are.
Your whole community, everybody.
Every post that you're doing, it has been it's been in our family conversations. So thank you.
And another one with that saturation is you can take a refrigerant tank, put one in a refrigerator, put one outside, put one in a room, and then they can see that pressure change. And for when people get to see that happening, it's powerful for them to actually see that difference.
Yeah, the visual.
Yeah. Right. So then we'll take a look at the refrigeration cycle, right? And so I've spent 5 years of my life as a technical trainer with Copeland. So I always start at the compressor. Different people start at different places, but I start at the compressor. And remember, I like things really simple. So let's start with the compressor. What do we do in a compressor? We compress.
We compress something.
And that's all we do is we compress a vapor, a refrigerant vapor, right? That's it. We compress.
In its simplest form. Absolutely.
That's right. So when we compress that vapor, our pressure and temperature rises, right? When we raise the pressure, we raise the temperature. So I want to separate those two a little bit and just look at those two individually, and let's look at pressure first.
Okay.
If I raise the pressure, and I had a law of physics that said high pressure goes to low pressure. I've got one of those, Ty, thanks to your videos.
Great way for them to see compressing. Like you compress it, and the volume decreases, and you can see the temperature and the pressure rise. And
that's right. Love it.
Fantastic visual demonstration.
So the highest pressure is inside that compressor, right? That last point of compression.
Right.
The lowest pressure in that system is where that suction line dumps right back into that compressor shell. So I've got a flow of refrigerant from high pressure back around to low pressure. Right.
Absolutely.
I've heard people argue and call that a pump, and for the most part, I don't like that. It hurts my heart because you pump liquids and you compress vapors.
Okay.
But what was it I said yesterday? We don't call it a pumperator.
Yeah.
All right, and then why do I need the temperature to rise from there? I need the temperature to rise because hot goes to cold. I have to get it hotter than my, keep this a simple air to air simple. We have to get that temperature of the refrigerant hotter than my outdoor ambient temperature. So the heat will leave the refrigerant, go to the air, and be discharged.
Okay.
Cool. Then we come around to the metering device where we lower the pressure and temperature of the refrigerant, and you have to get that pressure lower than our load, right? So I like to ask people here, I'd like to do air conditioning and refrigeration here. What would you consider the load to be in air conditioning? Just keeping it in its simplest form.
Air,
right? Because everything in the room gives off its heat to the air, brought down turned up, and moved through the evaporator where the heat exchange takes place. What about refrigeration? What's my load there?
Depends on what the condition that it's introduced into.
Could be glycol, could be beer, could be ice cream,
could be.
I still say it's air, because that product gives off its heat to the air, and the air is moved through the evaporator coil where the temperature is exchanged.
There we go.
Or the heat is exchanged.
Sure.
Right. And I like to stress that to point out that airflow, we talked about that before we came on air. Airflow is extremely important in every application, right? We measure it in air conditioning. We don't necessarily measure it in refrigeration, but we can still look, observe, make sure that the coils are clean, make sure product isn't stacked in front of it, make sure that there you go, product. Make sure that it's got clearances away from the wall so that the air can be moved through there. So that product gets off its heat to the air is moved through the evaporator, heat exchange is taking place. What you got, Ty? You're dying.
Yeah, when they have that line that says "Do not stack above here," I think a lot of people see that as a challenge. Like they have to exceed that. They have to block that up as much as possible.
I agree with you. All right. And another thing on this cycle of refrigeration right here is we discharge out of the compressor into the condenser and what line?
Discharge line.
Discharging.
Discharge into the discharge line. So what is the state of refrigerant leaving the condenser?
Liquid.
Into what line?
Into our liquid line.
We compress with a compressor, we condense in a condenser, evaporate in an evaporator, discharge into the discharge line. We're liquid in the liquid line. Does that mean we kind of name our components for what they do in our industry for the most part?
Absolutely. Spencer, I'm glad you're joining us. These are the reasons we do this, right? So we love to get back into the fundamentals, because if we can understand the fundamentals to the point to where we can help someone else understand the fundamentals, then we have actually learned that. I know it seems simple, and there's probably people in the audience going, yeah, I know this refrigeration cycle. But we have to step back and go, yeah, but when did we learn the cycle? And how many times have we sat back with another instructor just to make sure that we haven't missed something that we should have been utilizing all the time? So even though it is back into the fundamentals, the very basics of what we do, sometimes it's the most important things that we do. So Spencer, I'm glad you're enjoying this. We're actually going to get a little bit deeper here in a minute and start adding some additional components. And I think you're really going to like this, because when you think about this refrigeration cycle, this is the refrigeration cycle that you as a technician will encounter the rest of your life. Any piece of equipment that you work on, because once you make that move from air conditioning into refrigeration, it's typically because I just finally learned refrigeration that I've been working with the entire time I've been in the industry. So a lot of times we're shown the refrigeration cycle, but we're never explained that this refrigeration cycle will follow you the rest of your life. And when you understand this diagram right here and what happens on this, you'll be able to work on the smallest of refrigerators to the largest of freezers.
Yep.
We all operate in the same principle. So thanks for joining us, Spencer. We're glad you're here with us.
Yeah, Spencer, also keep in mind what I was just saying. We kind of name our components for what they do. So if you run across something that you're not familiar with, not exactly sure what it's doing, find the name of it, and that will give you a hint as to what's supposed to happen.
Yeah.
That was huge to me when I first started out running service out there by myself.
Yeah, absolutely. Eugene Silverstein always says, when you get multiple words in an item, just read it backwards. It's going to tell you what it actually does. All right. That liquid line is a line with liquid. A suction line is a line with suction.
Yeah.
That thermostatic expansion valve is a valve that has expansion from something thermostatic. And so keep that in mind as we're going forward. Externally equalized TXV boosted eco. I don't, maybe we'll see how far we get along in this. If not, we can definitely got some follow-up and educational content where we can dive a little bit deeper into externally and where that balance point connects.
Yeah, in my full-blown class, I actually have that in there, but I do not in this.
Let's do that real quick. I want to make sure that everyone has all the resources to connect with HTPG for refrigeration training going forward. Because remember, this is just bits and pieces of a full-blown refrigeration course that we want you to have access to. So this is just a contact form. If you're interested in scanning that QR, I know David's got another one here in the presentation with direct access for him to learn about the training courses that they have available through HTPG. So I'll make sure that I've got the web address as well for HTPG, because that's what we want to do. We want to get you introduced into things and then follow up and learn deeper about all these different aspects of our industry.
All right.
Okay.
So now we're going to complicate it. We're
Yeah.
going to make it complicated now.
Okay. This is a great one, though. So I think, George just mentioned that, this is good content. Right here is where it's going to turn into some great content. I promise you.
Right. So this is going to pull together what we just looked at and then that one line chart. Hopefully, that's what it's
Okay.
designed to do. So
Okay.
this is a pH diagram. The curved line that starts towards the bottom left and goes up and curves around and comes back down to the bottom line again. That's
counterclockwise.
Right. That's my refrigerant saturation line.
Okay.
So everything that's inside that line is refrigerant changing state. It's saturated. Everything to the right towards where that red arrow is in this particular picture is going to be a vapor. And everything to the left between the numbers 5 and 6 and the pressure line. So everything to the left of that curved line is going to be all liquid. Okay.
Okay.
So we're going to start at number 1, and that's
Yep.
where my vapor refrigerant enters the compressor, and it's compressed, raising the pressure and temperature. So that's why that line goes from 1 to 2 on a slight diagonal, and it's raising in pressure and temperature.
Okay.
Then we leave the compressor going from 2 to 3. So as soon as we leave the compressor, we start losing sensible heat, superheat out of that vapor. We start losing as soon as we leave that compressor.
Yeah. If you don't believe that, go touch it.
Absolutely.
I probably
It does not take you long to look at it.
Right.
Right? So then we enter the condenser at 3.
Mm-hmm.
We're entering the condenser at 3. So my vapor reaches saturation. So I've developed that first drop of liquid. So remember, once I develop that first drop of liquid and I'm in a mixed state, liquid and vapor together, saturation, my temperature no longer changes. So now as I'm going from 3 to 4, I'm going back and forth through that condenser circuit. I'm developing more and more liquid as I go through.
So I'm on that horizontal slide that I was showing on the previous screen.
Yep.
Right? I'm just making a transition at the minute.
Yep, that dotted line.
Mm-hmm.
Now I'm gathering more and more liquid. 4, I am all liquid, and I subcool that liquid. Right? Now I take sensible heat out of that liquid. 5, notice from 5 to 6 is a straight drop down. So that's going to be my metering device.
That's where we're going to change state.
That's where I'm lowering my pressure.
Mm-hmm.
And when I leave the metering device, I'm already saturated. It's mostly liquid, but there is some vapor there already.
Mm-hmm.
So I enter my evaporator as a saturated mix. I start absorbing heat, causing it to boil off, gaining more and more vapor, less and less liquid, more and more vapor. At 7, I'm all vapor, a superheat vapor, and I'm going back to the compressor. And I got ahead of my numbers here, but that's what's happening.
Absolutely.
Mm-hmm.
Well, I think it's important for us to discuss that because a lot of people will see those charts and not know exactly what we're doing, especially if you think like I do and that almost everything goes clockwise. And so you have to step back and relook at it for a minute and go, oh, this is where I'm raising temperature. This is where I'm lowering temperature.
So the point between 3 and 4, and just to keep it simple, 6 and 7 are my dashed lines that we were looking on that one line chart.
Exactly. Okay. Very good explanation. Any questions from anyone at this point as we continue moving forward? I hope that explains our pH diagram a little bit further.
And then our states of refrigerant throughout that entire cycle.
Okay.
Right? So we need to use a thermometer and a pressure gauge to determine what our states of refrigerant are within that cycle. And if we can do that, as you were saying, we can troubleshoot any mechanical system out there from the largest to the smallest.
Yeah, absolutely. I used to do an industrial air conditioning refrigeration class for a large steel manufacturer. And so I would go in with mechanics, very mechanically inclined folks that had never worked on air conditioning or refrigeration equipment in the past. They may have changed motors. They may have changed filters. They may have done some of the non-refrigeration circuit components, but they were never introduced into the refrigeration cycle. And on day 1, I would bring in a little refrigeration trainer that's a very basic with this principle right here. And then I would walk them around and I'd say, show me the largest compressor that you have seen in this facility. Take this diagram with me. Take a walk take a tour into the facility, find this largest compressor, because they always see these great big large compressors. Many of them change motors on them. And I go, okay, start with the watt line coming out of the compressor, exactly like you said, and let's walk through this circuit. And before we know it, they're standing here looking at 100-ton refrigeration circuits going, that's all? And go, that is.
Yep.
Yeah, that's it. We may add some extra things along the way, but my lawnmower runs on the same principle that my vehicle runs off from, that the same principle that my backhoe runs off from, that the same principle that largest train runs off from. It's just the ancillary items that help make those more efficient that we sometimes look at and go, oh, I don't know what this is. And on all actuality, it's the small things that we're paying attention to and not the larger things that we already know.
Yep. Awesome. So keep in mind, so if we're looking at this diagram right here, that condenser and that compressor, they're sitting outside if it's a split system. That evaporator and expansion valve are on the inside, right? So if I'm hooking my gauges up, what are they really telling me? So I get a pressure reading. What is that really telling me?
Saturation.
What my refrigerant's doing.
Yep. Only thing that's telling me, honestly, in my opinion, is at what temperature I'm changing state in each coil. Exactly. It's not telling me if it's right. What should my pressure be? I don't know. I need to know a whole lot more information before I know if it's right or not.
That's right.
There's a ton of information I have to know.
Yeah, it's exactly like Patrick Murphy said earlier when we were talking about voltage, right?
It's good. Yeah. Good is not a number.
Right. All refrigerant pressures are good in the right scenario.
Yeah. So it's important to understand because, yeah, I think we've all probably had conversations like that, if not those questions. What are my pressures supposed to be? I can't tell you unless you give me a ton of information.
Absolutely.
All right. So now I'm going to shift gears. And what I do in my full-blown class here is I start with the compressor, and I will go through. I will actually go through these four components we just looked at: the compressor, condenser, meter and device, and evaporator, and do a little bit deeper dive into each one of those. How do they do their work? Right. And then go through that, and then I'll finish the day up with additional components where I start looking at components that are not in that basic refrigeration cycle.
Exactly.
And I try to spend a little bit more time on what you would see in a refrigeration cycle or refrigeration system versus an air conditioning system, such as an EPR.
There you go.
An evaporator pressure regulator. So
say it backwards.
Yep. Regulate pressure in the evaporator. That's what we do. Right?
That's right. And if you notice, like if this diagram looked comfortable to you and you're an air conditioning technician, we have now become refrigeration technicians.
Yep.
That's all we've done. So,
and in looking at, we're just controlling pressure. If we control the pressure, we control temperature, right?
Mm-hmm.
That's why we have a PT chart. That's why the laws of physics work for us, is because we can control the pressure and saturation, and it's all tied together. So my EPR controls the pressure in the evaporator. In this example, I've got multiple EPRs controlling multiple evaporators with one compressor. So again, I can't see my numbers very well, but I've got a...
Sure. So we got a minus 20 in our frozen meat section. So remember, this is the same refrigeration circuit that we were looking at in air conditioning. We've just added some additional components to it. The primaries didn't change. So we've added 3 separate EPRs for 3 separate circuits so that we can manipulate the pressure. When we manipulate the pressure, just like you're saying, we manipulate the temperature, especially our saturation. So on our first one, we have the pressure set for this particular one at minus 20 degrees Fahrenheit for frozen meat. The middle one we have at minus 30 walk-in freezer. That'd be my ice cream freezer. Oh, no, it's at minus 35. So minus 30 is just it's a deeper meat freezer. But then our third one is a minus 35 for our ice cream, but all working on the same refrigeration circuit that we encountered with that air conditioner.
Right. And I don't know, really take care of that ice cream one, because that really, that's near and dear to me. It's keeping that ice cream nice and frozen. And then a CPR crankcase pressure regulator. It regulates the pressure in the crankcase of the compressor.
Got him going, Ty. He's on a roll. Thank you, Eugene.
And that's all. Well, in the class, I say, so what do you think we do with the CPR?
Yeah.
Right? Because I've gone through for half the day talking about we name our components for what they do. So
What they
I'll ask,
actually do.
what do you do? Right?
Yeah.
Well, that's what they do. Is it just controls the pressure back to the compressor. It looks very similar to the EPR, but my pressure tap's on the different side.
Sure. It's still just a pressure control.
Yep. I'm trying to regulate the pressure back to a compressor. So when we get into lower temperature applications, my compressor may not be designed to work with a warmer evaporator. So let's say we're coming out of defrost, I could very well take it outside of its operational, call it operation envelope. So this tries to keep it within that operation envelope. That's what this is designed to do.
Yep. Helps maintain current on the motor part of our compressor, so we can maintain exactly the operating envelope, not just for the refrigerant side, but for the electrical side as well.
Yes, sir. Yes, sir. So, and that's what I've got for this. And this is scan the QR code that will put my contact information straight into your phone. If you're up for that punishment, you're welcome to reach out to me. It'll have my email address, my cell phone number. You can probably be best to text me first and tell me who you are, because I probably won't answer an unknown number.
Right. Absolutely.
But I will absolutely be happy to talk to you, let you know where my schedule is going to be. Next week, I'm going to be in West Palm Beach, Florida, Miami, Florida, and Fort Myers, Florida, Tuesday, Wednesday, and Thursday in that order.
Wow.
So with this full-blown class, actually, this particular class.
And how long is the full version of this?
This class is 4 hours.
Okay.
And it's good for a whole slew of NAEP continuing education hours.
Okay. Absolutely. Any questions from the audience while we're right here? Any of the slides that we would like to go back and rediscuss any further? Because that's the end of the slides, isn't it, David?
Yes.
Okay. Ty, is there anyone that you would like to go back and spend a little bit more time clarifying?
Oh gosh, I could talk about this all day long.
Yeah. So let's back up, David. Let's go back and grab one of our particularly.
Go back to the crankcase pressure regulator.
There you go.
So that one, gosh, I've put in so many of those, especially when you have out here, there's a lot of deer leases and things like that, and they'll have these systems off for a long time, and then they go to turn them on, and then your compressor overloads, and they're thinking there's a problem with it. And so these crankcase pressure regulators, they just prevent that compressor from having too much pressure, prevent it from overloading. When you have that hot pull down, temperature of that gas is high, you're moving a lot more volume, using a lot more amperage on that compressor. And so you need to be able to take some of that load off of it. So just being able to say, hey, I got all I can handle right now, just hang back, and then feeds the compressor what it needs. And then as soon as that temperature, that box starts to drop, and that pressure drops, that valve's pretty much completely open. So it's just there for when it needs to be there. Great product to add, especially if a system is being cycled on and off, or you have a lot of hot product that you're bringing into a box. Those things are worth their weight in gold.
David, didn't you have a slide that had the CPR in the refrigeration cycle?
I did not. Well,
I think the one with the evaporators, I think actually,
yeah,
we could use that. I'm just thinking about using a single circuit to be able to help people understand. Yeah, okay. So let's look at it from this perspective. Let's talk about these grocery stores that we now have in the South that are all without power. And let's compare this to the air conditioning systems, because we got air conditioning technicians here with us today that are going to be going to homes where they're starting up their air conditioning under a full load. Now, many of our residential applications are used to that. A lot of them are designed for a significant amount of flow, but that is part of the reason we have such high amp draw on startup on a new installation, right? We're putting an excessive load on that evaporator. The air moving across that evaporator has a lot of heat in it, which is going to be raising the pressure The temperature is going to be raising the pressure on that suction line coming back to the compressor, causing our compressor to work very hard. A lot of times that's the reason we add hard starts as compressors getting a little bit weak. That's why we have capacitors to help work. Yeah, go ahead. You can correct me on that one because I don't like a hard start either, but I wanted people to understand what the hard start was actually doing, how it got its name. All right. It is trying to increase that torque because that compressor is under a significant amount of load on startup. Now we should understand why that load is there. But when people are looking at air conditioning systems and realizing what we're actually doing here, right? So we're putting a significant load on that compressor on startup. Let's compare that to a refrigeration circuit, this particular one right here. Say I'm a grocery store in the South and I have been off now for days because I have no electricity. And the entire inside, every evaporator on this circuit is now going to be at a high temperature with high humidity. It's going to have a heavy load when these fans turn on. Without an EPR on a refrigeration system, now we have a significant amount of heat, which causes a significant amount of pressure coming back to our compressor. So it gives us an opportunity to level out that pressure, especially on startups of refrigeration systems. So I know it's a jump between looking at an air conditioning and a refrigeration, but it's really not. And that's where we're helping understand what those additional components in that refrigeration cycle are there for. All right, now correct me on the hard start, Ty. I know where you're going.
Well, there's a bit of a difference in technology where we went from piston compressors that, they as soon as that compressor is turning, you immediately have a piston going up and you're compressing immediately right away. So there was, a lot of times we needed that start kit on there to, give that extra torque. It actually allowed more amperage into the start winding to give it the torque to get that compressor up to speed. But now that we're in the realm of scroll compressors, they start unloaded. They have a floating seal in there. They got a bypass port in there, so they're able to start unloaded. So it's like pressing the clutch in before you start the car. So the compressor is able to get up to speed before it's actually at the full pumping capacity, build up pressure, closes that floating seal. We're pumping our refrigerant, we open our check valve, and we're pumping on through. So now that we have the scrolls and how that works, putting a start kit on there doesn't necessarily benefit anything with the scroll. Now there's some cases to where if you have undersized wiring that can help prevent the lights from dimming, but really checking the incoming voltage is important. So that's where technology has changed, where we've went through the old days of reciprocating compressors. We could put a start kit on anything to now have a different technology of that scroll. And then when we see where a scroll compressor is going to need a start kit, is usually an indication of somebody that didn't pull a good vacuum or they got moisture contamination servicing it by not bleeding their hoses correctly. And that moisture with POE oil turns to an acid, starts eating away at the copper in the system. That copper floats around and it plates in the hottest part of that compressor, around the bearings, around all those moving parts. And now that scroll is having a harder time turning because all that extra copper and extra metal in there. So there's when you're going to need that start kit. Not that the compressor is getting weak or tired. It's that it's been abused for so long. Now we have some issues and other issues such as, lack of oil return or flooded starts to where we're actually damaging those bearings. So anytime I think, hey, there's a scroll compressor that needs a start kit, my first thought is let me do an acid test kit, see what's going on. Because there's acid in there. We could do an acid cleanup with that start kit and we can actually, extend the life of that system significantly versus just putting that one part on there and, seeing how it goes. At least you have the information to give to the customer. Hey, we have a lot of acid in the system. We put the start kit on, we're going, but we're going to have to address this. Would you like us to do acid cleanup? Do you want to start thinking about replacement? What do you want to do next?
I knew I seen that twinkle in his eye, David. as soon as I realized that I had mentioned hard start on compressor, I was like, I know. I'm in refrigeration, but when we start talking about air conditioning, it's a whole nother scenario.
So it's interesting how the floating seal and all that works. So they're actually designed in that scroll on the residential side to where if you have some flooded starts, that'll actually bypass and it tries to push some of that back out the way it came in, but it's able to handle a certain amount of liquid at startup, which is why you don't see crankcase heaters on them. But if you add a start kit on a system, now you have that extra torque of it starting. So if you have a scenario where you have a flooded start, now you have that liquid, you have the extra torque of that motor in there, and you're more likely to have a broken scroll set than you would. So if anytime you're adding a start kit on a residential air conditioner to a scroll compressor, I like to make sure that there's a crankcase heater on there. So anytime I've asked people that have broken scroll sets, I always ask, do you have a crankcase heater on there? And they said, nope. And that's usually that connecting factor in there. So it's just difference in how we do things. If you see commercial scrolls, they always have a crankcase heater because you got that 3-phase power. That extra torque is always there when that motor starts up. So they always have that crankcase heater on them to make sure that we prevent that refrigerant from migrating in there in the very first place.
You bring up a good point with scroll compressors. Both of you spending time at Copeland, seeing the transitions even in the refrigeration side. David, as we're talking about introducing scroll compressors into commercial refrigeration, a lot of people don't realize that. We've been doing it for quite a few years. I used to install a lot of Husband protocols, which were straight scroll compressors. Do our controls like the EPR come into play the same with scroll compressors versus reciprocating compressors?
You had to
Yes,
ask
I
me that
think.
question. I would think they would have to. Honestly, I haven't been out to look and see what they're doing necessarily right now with stuff.
Sure.
But I would think they would have to, because you overload, the electrical side of it just as much. If you get, if you don't have you said EPR or CPR, because I'm thinking
I
CPR.
said EPR, but I should have said CPR.
But I mean, you can still overload it. You can still have more coming back that it can handle and start, pushing things out that need to stay in the compressor, such as oil, and you can cause some issues without it.
Absolutely. Let's go back to that slide that has the 3 separate evaporators, because I think it's an important one for air conditioning technicians that are looking at refrigeration to see that we are still using the same circuit. This particular one here, we've added a couple extra things to our refrigeration circuit. One right off the bat. So let's think about, so if I was coming off from the compressor and I'm heading off to the left, I'm going to be condensing in that condenser. And I've actually added a liquid receiver onto this circuit. So could you help explain to some of our audience why we would need like a receiver on a circuit like this that's using multiple evaporators?
Yeah. A receiver basically's function is to receive and store liquid. So with the receiver, we ensure that we always have enough liquid to make sure we have only liquid making it to the metering device under all varying loads, indoor and outdoor loads, right? So that's the sole purpose of the receiver, is to store liquid and make sure we always have enough liquid in the system to feed the metering devices all liquid.
Exactly. So when we look at capacity of this total system, we have to make sure that our refrigeration circuit is large enough to maintain all 3 of those evaporators. But if one of them shuts off, well, now we've got a slightly oversized system and we just need to have a place to be able to store our extra liquid.
Yep.
So if you were looking at a refrigeration system and it had a receiver on it, that really is just that purpose, is it's an additional storage place for that subcooled liquid after it comes out of that condenser.
And that's a great topic too, making sure that we don't overfill that liquid receiver. I've seen it in the old days. A lot of people had these shortcuts for training. They would say, just clear the sight glass. Well, that's a shortcut, but it's not a good answer, because
Right.
if you're having a hot pull down and
Condition.
all your TXVs are opened up on there and you're blowing that refrigerant away fast and you're trying to clear that sight glass on a hot pull down, which I have seen people do or try to do many times, they're overcharging that system. And then when you get down to where it's in its load capacity, that extra refrigerant didn't have anywhere to go. It's filling up that liquid receiver, which it can handle it, until we go to automatic pump down. We shut that solenoid off, and all of that liquid goes into that receiver, and it doesn't have any place to go. So once it closes down, and then you got that temperature expanding because it's outside, I've seen those tops of those receivers, liquid receivers, blow out before, because that liquid expands, has nowhere to go. So when we're talking about some of these shortcuts, like clear the sight glass, we need to have more context to go with that, like making sure that we don't overfill our liquid receiver. It should never be more than 80% full. Should hold the entire charge of the system. And sometimes you got really long liquid lines, having to increase the size of that liquid receiver.
Yeah, absolutely. Great
And
point.
I think a fun one we have is misinterpretation of words. Everybody seems to call every valve now a king valve, but the only true location of that king valve is on the exit of that liquid receiver. It's a 3-position service valve, but specifically located on the exit of that receiver.
Check that
And
out.
I think it's funny when people call, they're like, "Oh yeah, that's a king valve." Like, nope,
Right.
that's a service port. Or they'll have a 3-position valve, and like, "Oh, that's a king valve." It's like, nope, specifically on the exit of that liquid receiver. That's the only true king valve.
Absolutely. Boosted Eco, appreciate you sharing that with us. You see more of those sort valves on the Hussmann single circuits. Completely get that. All right, we're at the top of the hour. If anyone has any additional questions or comments they would like to bring for us here, we'd be happy to answer them. There are a lot of people still hanging in with us, so obviously the fundamentals are still as important as anything in the industry, probably more important. And that's what we're here to do: is to help you be prepared for the classroom, be prepared for the service field, the installation field. If you have any further questions, make sure to get a hold of us. If you're an educator and you want to connect with us and spend some time learning a little deeper on all these topics, we will see you at the National HVACR Education Conference. Really looking forward to that. It's going to be a great time this year. We're going to have a lot of people hanging out. We were talking about those refrigerant PT charts. Another thing, I need to add the QR in here. If anyone is wanting to, for your classroom particularly, dive a little bit deeper into our refrigerants when we're talking about the PT charts and understanding those PT comparisons. ESCO now does have a R22, R410, R454B, R32 comparative PT chart for residential light commercial air conditioning applications. I'm sure we have a lot of refrigeration resources for learning at HTPG. Oh, Ty's got his. So I'll make sure to share that again. And I haven't seen any others pop up.
And I
So,
challenge you guys to always listen to somebody else's explanation of fundamentals, because there's 100,000 different ways to hear it. And the more that you hear it, the more you hear different people explain it. There's always little bits of information you can pick up in there. Like if you know David Harrell, he's brilliant. He knows so many things. And he's I agree with him. We have to focus on those fundamentals before we can talk about all this other cool stuff that we want to talk about. The
yeah,
cool components in refrigeration, like the stuff that's exciting. It all builds on that refrigeration cycle. So we can't move on to that next step until we really understand that foundation. And the foundation's cool. I mean, thinking about latent heat and how much energy is transferred in there. I mean, that's really awesome. And talking about heat energy. And did you know that music has heat energy?
tell me
No,
more.
because you get some really good music going, and you get all the moving happening. Next thing you know, the
Great.
temperature's rising, right? So definitely connected there, right? Just me?
Love
Okay, just me.
it. we're with you, Ty. We're right here. All right, everyone. We are so grateful that you joined us this week. We love having these conversations. If you have any topics that you would like for us to dive deeper, I encourage you to get a hold of us. My email, cbeck@escogroup.org. We'd love to know what you need. So we have all of the right people from the industry to keep you up to date, to bring the fundamentals and encourage the fun in the fundamentals. So let us know what you're looking for. That's right. We sure appreciate you very much. Oh, that's a great one. Thermoacoustics, Froggy. I'm glad you're joining us. See, I bet you're a fun person to hang out with. All right. So, Mr. Harrell, we sure appreciate you being here today.
Thank you.
Look forward to some more trainings in the future. And we're grateful to have HTPG hanging out with us this week on Did You Know? The ESCO HVAC Show. Bye, everybody.